Thank you, Sanne.
Well, good afternoon, everybody. I'm so sorry for the confusion here. The slides are on a Mac computer, so they look slightly different from when I made them. But I'm a PhD at the Spin Lab. I think Niels already introduced me. My background is actually in physics, and I'm working on applications, for instance, what Rob already talked about, the solar panels and 3D modeling. So I'm mainly a modeler and not so much of a data expert. And what I would like to talk to you today about is in the sciences and 3D, what we would like to do, what is possible to do, and what is actually useful to do, because there's a broad range in these things. And I would like to explore with you whether what we as scientists would like is also possible and even useful. So first, I really like to have the same definitions as you guys. So the first thing I'll do is talk to you about the differences between 2D, 2.5D, 3D, etc. And then about levels of detail, because I think this is a really crucial concept. Furthermore, then I will talk about restriction in the building modeling and consequently in environmental modeling. And then finally, I'll give you 3 examples of environmental models in different scale levels. So this is a really boring slide, but I think it's really important. So Rob already talked about that if we don't make the change to 3D, we'll stay stuck in 2D information. So 2D is the general map information that you already know. So there's an X and a Y coordinate, and this might have a value assigned to it, but it's not more intelligent than X and Y. Then 2.5D is what we work with a lot these days. This is XYZ data, but for every X and Y, there can only be one Z value. So if for instance, you picture a roof that hangs over, then that roof point is the only point. While below that roof, there are even many more Z points, and there might be a bench or something below it, but you can never see it because there's only one Z point. And actual 3D is for every X and Y, there are an infinite amount of Z's. Then 4D, this includes data about the time, so the change in the data values of X, Y, and Z. And then there comes ND. And ND, I've heard a lot of definitions about. I don't want to go into it too much, but this can be, for instance, metadata, model results, like colors on a 2D map, for instance. Then 3D can be used in many different sciences in many different ways. And I always look at it as a circular pattern. So you have data. The data you input into models, or you enrich the data. This data then turns into information. This information you can visualize. This visualization you hope for will in the end up in an act, or at least into a plan. But usually when you start planning or acting, you need more data. So the circle starts again. However, sometimes when you make a visualization, you realize that the information that you wanted to portray actually isn't quite the information that you're seeing. So then you would have to take a step back. And sometimes when you try to build a model, it turns out that you need more data. So this circular pattern can actually also run the other way around, though you hope most of the time to go forward. So this level of detail I talked about, we usually call it LOD or LOT in Dutch. It refers to the level of detail in which a building is portrayed. There are even more levels of detail here, but for this purpose, I don't think it's useful to go into them. So I will define the first 4. This picture already gives a nice overview. LOD1 is where you do know the building shape, the general shape, but then it's only brought up to a height point. So in general, it's just square, or it can be circular, but mainly it's spherical shapes, and there's not a lot of detail in it. If you go to LOD2, level of detail 2, you can already see a lot more about a building. So for instance, you can see rooftops, or you can see the fact that there are different aspects to a rooftop. You can even know the roof angles, or whether there's an extra construction on the roof, like a chimney or something. Then LOD3 is really the building in detail. So you know where the windows are, you know where all the antennas are. You still know, of course, the shapes of the roofs, but you really know in detail what a building looks like. This already looks very much like what we see in reality. And then finally, there's LOD4, and LOD4 also talks about the inside of a building. So, for instance, it talks about where the inner walls are and where the stairs are, and in this case, also where pictures and chairs are. This level of detail is usually only feasible for real building models that are built from scratch, rather than constructed from outside using GIS data. So why don't we have at least LOD3 for everything then? Well, there are two main restrictions. There's computer calculation speed. So if we have, for instance, for the whole of the Netherlands, we have this beautiful LiDAR data and AHN2 data, and in a lot of other countries, there's also a lot of LiDAR data available. However, to construct buildings, even in LOD1, takes a lot of time. So even though we have pretty much the amount of data available to construct LOD2, the amount of computers and the amount of calculation time that requires is too much, and therefore we cannot generate it. And another point is data availability. To construct, for instance, LOD3, where you know where the windows are, you need from the same XY point, you need several LiDAR data points taken from different directions, such that you can really reconstruct at a small scale the outline of the building. At this very moment, there are not enough of those data points available, and therefore we cannot in the near future construct LOD3. So now about the applications. This is the more interesting part. Applications work on different scale levels, and these different scale levels also require different levels of detail. So in my field, we define micro scale. Those are individual houses. You have meso scale, so those are neighborhoods, small cities, villages, that type of scale. And the macro scale, so that's either provinces or national or state level. My first example is going to be about the micro scale. I'm going to talk about insulation for a little bit. So what as scientists we would prefer to have is LOD3 information, especially because when you look at insulation of buildings, the location of windows is very crucial because the windows have a big influence on your heat flow in the house. However, as I already mentioned, for LOD3 we need a much more detailed information. And then even if we would have the LOD3 data, we still miss kind of the ND I talked about, so the current insulation state and the building materials that are used. Therefore, in many countries, and so in the Netherlands we have our own type, but the European Union also defined generalizations of building type, and those kind of inputs you use to model insulation in combination with the available LOD1 data. On the meso scale, I want to talk about noise and air quality modeling. So preferred here is LOD3 because you can make a very accurate sound model based on reflections off of windows versus to roofs versus to all these kind of things. And also you would like to have a lot of reflections in that. However, at this moment, it's only possible to work with LOD1. First of all, simply because that's the only thing we have. But second of all, if you want to, and we also only work with one reflection, because if we work with more reflections, and if we work with more accurate building models, the calculation time becomes very long, and it doesn't really make sense to do it anymore. And also, in many countries, the legislation prescribes that when you use sound models to see if there is sound pollution or air pollution, only LOD1 is included in those laws. So therefore, LOD1 is useful and preferable. And then on the macro scale, Rob also already slightly mentioned the wind turbines. For the wind turbines, we have a lot of 3D data inputs. So we need to know the wind turbine, the hub height, the wind speed at different heights depending on the hub height, and also the buildings and infrastructure that are around the wind turbines to accurately model, for instance, sound pollution or shade pollution, the energy potential, and the financial consequences. So when you look at wind modeling, you don't only need the building information, but you need a lot of 3D data and also many 3D models. In this case, for the modeling, LOD1 is quite sufficient because of the scale you work with, and also, again, to ensure calculation speed. However, to model with LOD3 is not very useful with wind turbines. However, what you do need to keep in mind, in the circle I showed you before, there is the modeling part, which I talked about most today, but there's also the visualization and communication part of the wind turbines in this case. And when you go to citizens and communicate results of your models, it is very crucial for their faith in your results, that they can really recognize their environment. And therefore, if you come with LOD1 visualization of their neighborhood and the wind turbines, you lose credibility, and therefore the people really need LOD3 visualizations, even though the models are only in LOD1. So in conclusion, in science, we always prefer LOD3. It's more accurate, and we always like the most accurate results. However, what is possible is technically only LOD1, unless you really go into the small scale and you do your own measurements. Therefore, visualization, you always prefer to go to the lowest scale level as possible, which as scientists we also prefer. However, this is not necessarily for modeling. And for the macro scale, only LOD1 is possible. And actually, if we're being honest, that's the only really useful scale. For the mesoscale, it's also preferable to use LOD1, but more accuracy can definitely be added by at least going down to LOD2. And especially if you go to the micro scale, then LOD3 is really important. And actually, I wrote down LOD3 plus, because you really need to go further into that, and you might actually have to resolve to local data gathering, which is expensive. I want to thank you for your time, and I'm going to go back give it back